Please welcome to the stage Kemal from Polar Signals. In front of. Okay, Kemal, hello, welcome.
Hello.
Now, a little birdie told me, Twitter, that you make mechanical keyboards.
Yeah, I do. I am very into custom mechanical keyboards, like fancy split keyboards.
Yeah.
Like pianos?
No, just computers. I'm not that fun. Sorry.
But what do you mean you make them, like from a kit, or do you make them from scratch? How do you do it?
There are kits, or like you can actually get a model, 3D print that, hand wire everything. There are open source firmwares. I asked for a TinyGo one. There isn't one. I would like to have one. Yeah.
I have a question. Is there like a technical, technique to make them louder?
Oh yeah, that is called switches, and more specifically blue ones. They are really clicky.
I'm sure. Do you work remotely? Do you work remotely or in an office?
I work remotely.
Okay, good.
But I used to work in an office
Okay.
with those guys, and everyone has like pretty loud mechanical keyboards.
Good noise cancelling headphones?
Yes, that's a must.
That's cool.
I love mechanical keyboards because I like everyone to know I'm writing an email, even if it's not to them. And what about the keycaps? Are you into keycaps?
No, I'm kind of a back-end guy, so
You're
I don't care
back-end.
about the front end.
You're
So
a back-end mechanical keyboard engineer.
Yeah, back-end everywhere. Yeah.
Excellent. Well, Kemal, I can't wait for your talk. So without any further ado, please welcome Kemal.
Thank you. Yeah. Hey everyone, just a little bit about me. Today, maybe first I need to speak about what I'm going to talk about. Today we are going to talk about building profilers for Go using Go. And a little about me, I work for a company called Polar Signals. Surprisingly, we build profiling products. This is actually how I look like on the internet. So if you come across this guy, she's my dog, by the way, 10 years old, and it's from her party. And on top of that, I maintain a couple of these open source project. Okay. Anyways, so I will put the slides and all the demo material into my personal website. You can check it out. And I always talk about Linux, profiling, those sort of stuff. And if you're interested on those, you can follow me on Twitter. So yes, let's talk about profiling. So profiling is as old as basically programming. I guess the first mention goes back to 1960s or so, when you check the Wikipedia, at least. So what is it? It's a sort of dynamic program analysis. You measure the memory you use, CPU, whatnot. And like, why do we do that? Like, actually, Bill explained that like better than me yesterday. Like, hey, Bill, I'm a fan, by the way. So why basically profiling is about like finding out the components or the functions that we're optimizing, or like basically understanding the program so that we can make it better, right? So but how we do that? So for Go runtime, it's actually like easy, right? You have Go tool profiling, just use that. But speaking on more academic terms, there are two types of profiling. One is tracing, where you actually capture all the events and aggregate them and try to make sense of it, which is really high cost. But there's another way, which is sampling. Rather than having all the events, you just aggregate them, and maybe every 10 seconds, which is a sampling duration, you collect them, and then you try to estimate the CPU usage from that. It's actually pretty accurate estimate, and when it comes to the overhead, it's really few overhead, like 0.5 or so. And the data is coming from a Google paper, which you can have the link here. So, like more on Go profiling overhead, Felix actually explained this like better than me in the previous GopherCon 2021. And he just like conducted an experiment, and he compared a lot of different types of profiling. But today, I'm going to talk about specifically CPU profiling, For that specific purpose, I built a tiny profiler. I call it Tiny Profiler. Creative, I know. And what it does, it profiles the whole machine, and it looks for specifically Go binaries and try to profile those. And since like Go is like super into pprof, we're gonna use the pprof format to output our profiles. So let's see that in action. Actually, okay. Yes, here we go. Is this the correct one? Yes. So it's in 2022. It's really hard to emulate Linux on a Mac. Unfortunately, that's why I am connecting to my machine at home using Tailscale. Super cool product, by the way. So let's see if our profiler actually works. So this script going to run the profiler for us. And we need sudo for that, which I'll explain later. So we just run our profiler. It's running. To just to create a demo environment, we are going to create a noisy tenant. And let's check if everyone, no, not exited. Don't do that. Come on. I knew this gonna happen. Can I build you? I can build you. Oh God. Yeah. This always. I haven't sacrificed enough, I guess. Are you working? Come on. Let's try this again, please. Oh, of course, you are also running. So don't test your stuff before your talk. So obviously, that's the problem here. Okay, this is hard to type on the stage. Okay. Come on. Keep doing that. Okay, let's check this one more time. Or just kill that, whatever. It's the same thing. Okay. Okay, let's try. Please, please, please. Yes. Yes, I skipped that a little fast. Can you see this? Yeah, okay. So these are the captured profiles from the whole machine. And from that, let's grab a random one. I hope it's going to be a good one. We are going to use pprof to symbolize. Probably you can see that. We grab that profile and we run pprof UI, just like yesterday, as Bill did. Okay, our profiler works. And it happened to profile NordVPN, which is a good thing. Apparently, NordVPN written in Go. So with that profile, you can actually check out what's going on here. You can do the top. You can check the flame graphs. In this case, yeah, we already seen that. But like, there's something wrong in here. You don't see any human-readable things, which I will talk about soon. Let's just make sure that we quit our demo this time, so because we will have others. I don't want to see that happen again. So where are my slides? Okay. So this was our tiny profiler. It works actually, do the same thing. We'll soon see what is made of. So usually profiling is an incredible tool that you already seen. You can do a lot of stuff with that. But there are some problems with like normal profiling apps. It's normal, okay. It is momentary, so you can only capture a point in time, and you get a snapshot of your process, and you need to do this manually, or you need to build some scripts to actually automate that and capture those snapshots. When you have that, like, you are missing a lot of points, right? Maybe there's an incident and you weren't there at the right time, at the right place, and you cannot capture those. So for that, there is another solution, which is continuous profiling. So as the name suggests, like, you continuously profile your running processes. So this is popularized by Google. There's a paper from Google called Google White Profiling, which they describe how they continuously profile their data centers, all their infrastructures continuously on their production workloads. So why they do that? It's actually simple, right? Development is not production, right? We are not using the same software, maybe not the same CPU architecture. Most of the case, the machines are not that big enough, like your laptop, for example. This is actually a lot of CPU cores, and maybe you are missing a lot of problems when you run it in a smaller container. Moreover, like, you are missing a lot of data, context over time. You have other observability signals from your infrastructure, for example. You can correlate that with your profiling data. So using those data, you can actually resolve all the incidents because you have more context, right? So eventually, you will save more money, because you will optimize your workloads. You will cut down the cost from your cloud infrastructure, for example. So that's why continuous profiling is a thing nowadays. According to our super scientific study, we can cut down like 30% of your cloud cost by using cloud profiling. But like, it's useful because like you can save money, as we already talked about. Like, you can understand the differences between your deployments, for example, or differences between your data centers, maybe CPU architectures, so that you can optimize for that. You can understand the incidents if something goes wrong. Especially this, for the last part, I really want to give an example of that. This is not actually a CPU profile, as we shown in Tiny Profile. This is a memory usage profile. This is a pattern that you see very likely in your infrastructure. Does anyone know what this pattern suggests? Okay. This is you can call it like truth solve pattern. This is actually an kill, because your process is exceeding the memory limits of the container and it's getting killed. So like with tracing or in metrics, you can't know what's actually doing that. Are you leaking a memory, or you change something and it's using more memory? You can't tell that. So, but if you have continuous profiling, you can actually reach that profile just before that incident happened, and you can just like check it, what's going on. So how we do this? pprof actually, Go runtime, creates those profiles, and you can just grab those profiles using a tool, and then you can just put it in a time series, and then you can actually check it out and you can like actually find what's going on in that point of time. So like to be able to do that, like we already talked about, sampling is cheap. You need to sample your profiles, and then you need to have a index over time, and you need to be able to query this fast. So you need to build specific software to do that actually. The scenario that we like go over on it one more time. You have a process, so each time you get and capture some profiles and aggregate them over time with additional context, and then you can just find out what's going on with any point of time. So again, gist of it, this is possible right now to do this on production with certain tooling. And we are super lucky because now we have this new technology called eBPF, which stands for Extended Berkeley Packet Filtering. The name suggests nothing about what this tool does, because it's like invented for filtering network packages, and then it evolved into a fully fledged virtual machine. That's why the extended comes in front of that. So how it works, in the kernel space, you have a process, you compile your program, and in the eBPF system, you have events, and you can attach those programs to those events. And those programs actually, in the runtime, when you load them into the Linux kernel, there's a verifier that actually verifies that your program doesn't have any infinite loops, you are not doing any harmful stuff, you have instruction limits, whatever, because like you are running this code inside the kernel with all the privileges. That's why you have the sudo in front of that demo. That's why this has come all together. There's a JIT compiler for these programs so that they can run fast, but yeah, again, everything runs on the kernel. Also, that's why right now this profiler can only run on Linux machines. But Microsoft's also working on a eBPF virtual machine for the Microsoft kernel, which is cool actually. So, another demo time. So let's see if we can manage to do this time. Okay. We have the next demo. Again, we need to be super user. This time, we're going to run Parka, which is a storage for profiling, and I will talk about it later. So we will start the tiny profiler and send our profiles to the Parka server. We will create that noisy neighbor again, so it can create some noise around so that we can profile. Okay, Parka, don't do that. Not you. I'm taking care of you. Yes, we know how to fix it. We're just going to kill everything. No, of course. Let's try. Yes. Okay, let's see what we have over here. No? Okay. Internets, please. Okay. No? It's slow. No? Come on. Can make sure. This is not the way you do it. Okay, but it worked. I don't know. Okay, so this is Parka UI. I hope you can see that. What this does is this is continuously profiling my machine at home and looking for Go processes. This is actually what Tiny Profile does. Then it grabs those profiles. Rather than writing them on the file system, it's just sending over those to Parka. Let's check what we have here. We have Parka itself. You can see the profiles. This is an icicle graph. Same thing with the flame graph. But we are polar signals, so that's we like ice. And we also have our noisy neighbor over here. Yes. So apparently, it's busy doing something on CPU, right? Some Fibonacci calculations. With this UI, rather than you just like having single profiles, you can see that we are continuously aggregating all those profiles, and you can actually also query them. Let's grab one of these. What is it? This is containerd. Okay, let's check what containerd does. It's running some containers, actually collecting some garbage, surprisingly. And you can actually, since we are focused on that, you can compare profiles. You can pick a point in here, another one here, wait for Parka the process, and you can compare the stacks. And the color coding suggests that we are like spending more time on doing these functions so that you can find out like what's wrong with your processes, and you can maybe optimize that. For this, I don't think you can do a lot of things. Maybe you can check out this NivGo GC flex from yesterday's talk, and you can optimize these things. Why not? So this is how Parka works. So, oops, it was fast. So let's dig into some code, if I have time. I don't know about time management. So I told you about, can I see? I can see my cursor, so I will do this. Can you see this? Is it readable? Okay. Light background actually hurts my brain, but I will bear that. So this is actually how you attach a program to a perf event, right? This is a perf is a subsystem in Linux to collect the perf profiles, basically. The resource usages, it's doing dynamic analysis, whatnot. And you subscribe to that perf event, attach this C function, and from that C function, you grab the process IDs, you grab stack IDs, and then you grab the stack traces themselves, right? So to do that, we have like actually two maps to aggregate. They are special structures. You can actually see over here how we define them. One is just a hash map, and the other one is a special type of map to actually aggregate the stack traces. So you ask kernel to give me the stack, and from that stack, you need to do this in a two-phase. You need to ask for a user space stack, then a kernel space stack, then you need to append them, and you need to send them over. You need to put them on the hash map so that we can read those maps in the user space. So it's a simple eBPF program written in C. You can actually write eBPF programs in Go as well. There are packages for that, but we prefer to use libBPF, which is where the community actually converges. For that, we have a special tool called libBPF Go. It's a thin wrapper around libBPF, which is a C library in the Linux kernel. As you can see that this is a C Go program. It's not pure Go. So what we do, we are using another tool chain and compile the program that we wrote, and we embed that into the binary itself. And using the libBPF Go, we actually load that module when we run this program. And then we load that program. This is the phase where the verifier runs and checks if your code is OK. And then we subscribe to the perf events for each CPU so that that program can run. When that program runs, like it populates all those maps, this is where we actually get the hang of our maps so that we can use them. So then you can specify the profiling duration, and by default, it's 10 seconds for now, this tiny profiler. So every 10 seconds, we run a profiling loop. What we do in that loop is we are reading from those maps, and we are trying to get the stack IDs and the collected stacks from those maps, which involves a lot of low-level binary reads. You need to know the byte orders, serialization between C structs and Go structs, a lot of details. And then we do a lot of bookkeeping, error handling, lots of edge cases later. We started to read the stacks, and to make this more efficient, we aggregate data in several maps and slices, and we collect samples until where we actually build the profile. So all those magic later, we build our profile, we convert that to a pprof profile, then depending on our writer, which can be a file writer or a remote writer, we write that pprof. There are, again, lots of edge cases to actually handle this thing. So when it comes to that, actually, maybe lessons learned. So C-Go is definitely not Go. Yeah, you can be sure of that. And actually, Yesterday, one of you asked to the core Go team what it takes to compile a CGO program, CrossCompile a CGO program. This is actually 300 lines of makefile that make that magic happen to link against like that eBPF CGO, using Clang to cross-compile, using Clang to compile that object, eBPF object, a lot of details. In this project, you can check out the makefile. I mean, it took a while to bring all these together. We can actually, you can actually cross-build this. We have containers for that and GitHub actions. So the whole shebang in the code base. So there are a lot of things like cross-compiling, reading data from the C space and synchronizing that to the Go space, lots of challenges. On top of that, symbolization is like harder than it looks, which I will explain in a minute. What you get from stack traces is just a bunch of addresses. And from those addresses, you need to convert that to the human readable format, and which is harder than it looks. There are lots of you need to understand elf, dwarf, orc, other fantastical beasts. These are all Linux terms. There's really hard to find documentation on these, which is my third point, so that you can understand what's going on, and then you can symbolize all those stacks. But we are building Go programs, and profiling Go is awesome. First of all, like you have built-in facilities in the runtime. Aside that, even using an eBPF program, it's like super easy to do this because Go itself is debuggable. Like kudos to the Go core team for making the conscious decisions around that. Stack unwinding is super easy. Symbolizing is super easy with Go. So when I talk about stack unwinding, what does it mean? This is a stack snapshot. That's actually a trace that you get from Go or any running process. At the bottom of this stack, your eBPF program runs, and you get an address. And now you need to build up a stack trace from that address. You only have the program counter. To be able to do that, you need frame pointers. And Go has them by default. That's not the case for most of other compiled languages because they would like to use that additional registry for performance reasons, which is just 2 or 5% or something. But people like to optimize prematurely, and it's really hard to do this with the other programs. But Go being a nice citizen, and it's super easy to unwind the stack with the frame pointers. So when you unwind the stack, this is what you get. This is hexadecimal code. I don't know about you, but I can't read this. I'm not that mega savant. So I need human readable things. So to be able to do that, you need to read Go binary, and you need to read specific sections, find those symbols corresponding to the program instructions, and symbolize for the human readable format. So dwarf stands for, I don't remember what it stands for, but there are debug information in that. And people tend to just strip those from their binaries because they want like smaller binaries, but they don't realize that they are creating problems because now your binary is not that observable. But Go being, again, nice citizen, there's Go PC line tab, stands for program counter line table. There's a specific section. Go uses this when a panic happens. It just uses this to unwind the stack and symbolize it, so you cannot just strip that section because your Go binary runtime will break. Just having that section symbolizing the stack traces are easy. There's even a package in the runtime for that. You just read Go PC line tab, grab those program counters, and just get the name of the functions. You can all find those things in the code itself. I think I need to speed up, so I will go to the Parka bits. So Parka is totally open source project. You can go and contribute and grab and read the code base itself. Tiny Profiler is a reduced version of Parka agent, which is a component in the Parka project. There's a server and agent, and Parka agent written in eBPF using eBPF, and it's used to profile Kubernetes and systemd resources. It supports C, C++, Rust, any compiled languages that's as of now, but we are working on adding other runtimes and whatnot. But Tiny Profiler is a small version of that, and it's just profiling the Go itself. Again, Parka, neutral governance model, even though Polar Signals created that, it's inspired heavily by Prometheus. A bunch of us are Prometheus maintainers. That's why we just carry out the philosophy. It shares the same multidimensional model. It's a single statically linked binary. You can just drop that in your cluster or your workload environment, and you can start collecting the data, and you can have that nice UI to just check out your profiles. It has a built-in storage to optimize for storing profile data. And then we have Parka Agent, again, another open source component. It's an eBPF-based profiler. If you are interested in the details of a profiler, runs on a production, just go and check the code base of Parka Agent. You will find all the links in there. On top of Tiny Profiler, Parka Profiler do some magic around C groups and using discovery systems from Kubernetes and other container runtimes and enrich the data that you have. So you can drop the Parka agent in a Kubernetes cluster, and it will just collect everything in there. Kubernetes consists of like Go programs, so you can just immediately see what's going on under the hood. So Parka agent roadmaps, like we really want to add other languages, like Ruby, Python, those type of dynamic languages. We would like to add additional profiles to check out heap, allocations, and memory, which is not easier as it sounds, but we need more contributors, we need more users, so we need to build community, and we need you. So if you are interested, just grab a container, run it, and give it a shot. If you are interested in the details, it's all open source. Check out and contribute. So, shameless plug. So, about the symbolization, I wrote these 2 blog posts. Like this is just tip of the iceberg. If you would like to check out more details on this topic, you can go and read these blog posts. Again, like I will share my slides. So all tools that I use, if you want to take a picture, it's the good time, I guess. I have a new phone. You can actually click those links. It's super technology. Okay. Thanks for listening. This is how you build a Go profiler using Go.